So welcome everybody to the final plenary session for this event, which is the third event out of four, and I will be chairing this session. I'm Riccardo Sapienza from Imperial College London, and then at the end, I think Emanuele will say a few words about the future of this event. I won't spoil the surprise. So now the next speaker is Professor Robert Boyd, which I think many of you know already. He's the Canada Excellence Research Chair in Quantum Linear Optics and Professor of Physics at the University of Ottawa. And as you know, he has been working in many different fields, from nonlinear optics to quantum optics and metamaterial and EMZ. And then I would say that he's one of the father of this field. And so it's really a privilege to have him here today. And Robert, if you want, I can't see your video. Can you share your screen and then everything?
Yeah, let's do that. Let me go to full screen on my presentation view. And I think that
that's perfect.
That should do it.
Yep.
Okay, so Riccardo, first of all, thank you for the very, very kind introduction. I'm very, very pleased to have been invited to participate in this workshop. So my title is Nonlinear Optics of Time-Varying Media, but I put in parentheses, especially Epsilon-Near-Zero Media. So, so of all the things we've heard about time-varying media, let's add Epsilon-Near-Zero to it. Still trying to get everything set up. Okay, so first of all, let's okay, so not Epsilon-Near-Zero materials, also known as zero index materials, epsilon being the dielectric permittivity. So we know that the wavelength of light is given by the vacuum wavelength divided by the refractive index. So there is a significant lengthening of the wavelength in a Epsilon-Near-Zero material. We also know that the phase velocity of light is given by c over n. So as n approaches zero, the phase velocity becomes infinite. These two facts taken together tell us that for n approaching zero, the field oscillates in time, but not in space. Oscillations are in phase everywhere. So yes, this condition is compatible with Maxwell's equations, but it's a limit that we rarely think about, the limit in which the refractive index vanishes. Now, there's some very, very intriguing physics that occurs in these Epsilon-Near-Zero materials. For time reasons, let me just point out one of them. It's that radiative processes are modified in Epsilon-Near-Zero materials. And in particular, the Einstein A coefficient in a medium is given by the refractive index of the medium times the usual A coefficient for an emitter in vacuum. So that means we can control and inhibit spontaneous emission. Einstein B coefficient, well, that gives us the stimulated emission rate. You find that this is given by the vacuum value divided by the product of the refractive index and the group index. The optical gain under many circumstances is very large. Implication, if we can inhibit spontaneous emission, we can build thresholdless lasers. Other implications that we expect superradiance effects to be pronounced in ENZ materials, because every atom in the medium sees exactly the same phase of the electromagnetic field. So they can't help but emit cooperatively. Okay, but what about nonlinear optics? Let's turn our attention now to nonlinear optical properties of Epsilon-Near-Zero materials. First, just a big high-level view of this. First of all, we know that nonlinear optics is important. There are a whole bunch of things you can do with it. However, the nonlinear response is usually much weaker than the linear response. So we have all these potential applications that are very difficult to implement. Over the years, actually over the decades, people have been looking for ways to enhance the nonlinear response. They've looked at resonance interactions, plasmonic systems, electromagnetically induced transparency, and metamaterials also known as composite materials. Now, the approach that my group has adopted is to use Epsilon-Near-Zero materials, and metamaterials that contain an Epsilon-Near-Zero material. So that's what I'll be talking to you about for the most part. Now, why is it that Epsilon-Near-Zero materials tend to have a very large nonlinear response? Well, here's a simple intuitive argument for why the ENZ condition is of interest in nonlinear optics. And I'll just remind you of the standard relationship between N2 and Chi3. And if you've forgotten what N2 and Chi3 are, I have a footnote here that tells you these are coefficients in a power series expansion. But we note that there's the refractive index and the real part of the refractive index in the denominator here. So under Epsilon-Near-Zero conditions, N will become very small, leading to a very large value of N2. And we should think of this, that Chi3 is sort of the fundamental reaction of material to electric field. N2 tells us how this nonlinearity shows up in a particular experimental context. Okay, so I've given you some reasons to think that Epsilon-Near-Zero materials would be of interest. So how do you choose an Epsilon-Near-Zero material? Well, there's a bunch of things to do. You can look at electrical conductors. And in fact, all conductors display ENZ behavior at their plasma frequency. In fact, many metals are very well described by the Drude formula. And just by inspection, you can see that the real part of epsilon will vanish at a frequency that's given by what we call the reduced plasma frequency. So that's fantastic, except that we don't have plasma frequencies all over the spectrum. Noble metals have their plasma frequencies of the UV. Some semiconductors can have ENZ behavior throughout the near infrared. Okay, but there's another way of doing ENZ. That's to use electrical insulators, because these insulators show Epsilon-Near-Zero behavior at their phonon resonances. So these phonon resonances tend to be in the mid-infrared, let's say. Third way is use a metamaterial. This requires that you go out and find a friend who knows how to build metamaterials, and you design one that will have its Epsilon-Near-Zero behavior at the wavelength that you care about. And I've made it almost sound too easy. For any material system, we want low loss. So we want the imaginary part of epsilon to be as small as possible at the wavelength where the real part of epsilon vanishes. Well, the real part of epsilon vanishing is usually in a region in which there's a rapid change of epsilon with frequency, and that means that the imaginary part of the refractive index is going to be significant. So that's the real challenge. Okay, now most of my work has been done using indium tin oxide, ITO. I don't want to read this to you. ITO is also described well by the Drude formula. The sample that we are using has its plasma frequency at 1.24 microns. I say the sample that I'm using because indium tin oxide is not stoichiometric. So if you get it from different sources, your Epsilon-Zero wavelength is going to be different. And of course, the whole world is not built on indium tin oxide. The group of Vlad Shalayev, who we heard just earlier today, has worked on the material aluminum doped zinc oxide, AZO, which is my view. ITO and AZO are both good materials, and they sort of complement one another. Okay, so here now I'm going to really summarize a couple of years of our work on the nonlinear response of indium tin oxide. So the first thing we did was get a sample, do ellipsometry. We determine the imaginary part of epsilon and the real part of epsilon, and we find that the real part of epsilon vanishes at a wavelength of 1240 nanometers. We then perform a Z-scan measurement. We measure N2 as a function of wavelength near this epsilon-near-zero wavelength. We find that there's a significant peak in N2 at the epsilon-near-zero wavelength. And it's large too. This value of N2 can be 300,000 times larger than that of silica glass. Perhaps more surprisingly is that the overall change in refractive index can be as large as 0.8. Here is the refractive index as a function of the intensity. This work here was taken at lower intensity, so we're in this region down here. And finally, indium tin oxide displays sub-picosecond response. So here's the result of a standard pump probe experiment. So sub-picosecond response means that it has a terahertz switching rate. So what do you do once you have your indium tin oxide? Well, we made a metasurface out of it because this is a step in the way for applications. So we made this metasurface by putting gold antennas on top of indium tin oxide. Now, the way you understand this is that, well, the antenna has a resonance. You want the resonance of the antenna to be at the same wavelength as the resonance of the indium tin oxide. Indium tin oxide supports two surface modes. One is a short range surface plasma and polariton. The other is a long range surface plasma and polariton. We are working on this resonance here in our work. Oh, and here's what we found. Here again is N2, measured as a function of wavelength, theoretical fit. You see that N2 can be either positive or negative, which could be used for some applications. We can move this curve back and forth by changing the length of the antennas. The largest value of N2 that we got in this work was 20 million times that of silicon dioxide. So highly, highly, highly nonlinear. Okay, now we turn to what the talk's supposed to be about. Let's talk about some applications of time-varying epsilon-near-zero materials. And the first one, I just love to show this because it tells a story. So I think we've all seen this scene from Star Wars. Here's a holographic image of Princess Leia. I claim that today, holographic techniques have not developed to the point where we can have video rate changes of holograms. So our goal is real-time holography with video or much faster refresh rates, and we're going to use indium tin oxide to do it. So here is the experimental setup. First of all, the object is just a OAM beam. It's a pedal beam. So the way holography works is that you interfere the signal beam with a reference beam. That forms an interference pattern on the indium tin oxide. This interference pattern will live for something like a picosecond. During that picosecond, you can send in a readout beam. Readout beam scatters off this diffraction pattern and produces a reconstructed signal beam and the conjugate of the signal beam. And here it is. Here is the readout beam generating the reconstructed signal beam and the conjugate of the signal beam. So this work is still ongoing. Next topic I want to talk about is adiabatic wavelength conversion through time refraction. There are situations, for example, in telecommunication, in which one wants to shift the wavelength of a information carrying beam by maybe tens of nanometers. Now, we do it using time refraction. Let me explain what we mean by time refraction. We all know about space refraction. This is what gives us Snell's law. The light leaves the region of index N1 and enters the region of index N2. In this process, the frequency stays the same, but the wavelength gets changed. Now, we have something called time refraction. This is refraction, but in the time domain. Here is a beam of light inside a material, and at a certain moment of time, the refractive index changes from N1 to N2. In this case here, the wavelength is going to remain the same, but the frequency changes. So this is what people have been calling adiabatic wavelength conversion. Now, should not be a mystery. This is an alternative way of understanding what has long been known and called self-phase modulation. We get a change in the frequency of a beam, which is given by the time derivative of the nonlinear phase shift that we impress on the beam, and the nonlinear phase shift is just n2 times I times omega over c. So if you have a pulse, the intensity is changing in time. So here's the experiment we did. We have the output of an optical parametric oscillator. We divide it into a probe beam and a pump beam. We have a delay line here. This delay line can control the timing of the pump beam and the probe beam. So we can delay the pump beam with respect to the probe, we can advance it. Here's our sample of indium tin oxide. We allow the probe beam to go through the sample under the presence of the pump beam, and we measure the spectrum using an optical spectrum analyzer. So here are the results. Experiment, simulation, very, very good agreement. Here is the frequency shift as a function of the delay between the arrival time of the pump beam and the probe beam. And these results from a number of measurements are summarized here. This gives the maximum wavelength shift as a function of intensity at the timing that gives the maximum delay. And you see that we can shift things by maybe 75 nanometers. So I said already, the application here is for wavelength division multiplexing for telecom. So we are still working on this project as a joint project with the group of Alan Wilner. Alan, of course, understands telecom. This is what he's trained at. So we've done a couple of work with him, presenting follow-up work on the project I just showed you. Okay, other project that we're working on, ultra-fast pulse measurements by time division, single pixel imaging. So if you want to have a time varying medium, you need to do ultra-fast pulse measurements to see what's going on in the material. Now, we were exploiting the analogy between the spatial domain and the time domain. So single pixel imaging is now a standard method for image acquisition, and we want to apply that same concept to ultra-fast pulse measurements. So let me remind you how single pixel imaging works. Here's the photodiode. It is not an array, that's why we call it a single pixel. We can control the illumination pattern that falls upon the object we want to image. We simply measure what the transmission of the object is to this particular structured probe beam. We do this for many different structures on the probe beam, and we can build up the image that way. Now, in the time domain, which is what we're working on now, we have a temporally structured probe beam. So here you have a beam you're trying to analyze. Here you have a probe beam. This beam interacts with this beam, and they fall on in some nonlinear medium here. And we've used electro-optic sampling, sometimes some frequency generation. So we look at the interaction of these two beams. It falls on the photodiode. This photodiode is slow. It does not resolve the individual peaks here. And I guess that's the whole point. Using a slow photodiode, we were able to do sub-picosecond measurements of this beam. So laboratory implementation. Here is the zinc telluride crystal. This is what actually mixes the pump beam and the probe beam. then what is leaving here falls onto a zinc, falls onto a photodetector. Key issue of how this works. This is a digital micromirror device. When a plane wave falls on this at normal incidence, it diffracts into the first order, but the path length difference is different for different points on the surface of this grating. So we started with a single laser pulse. We end up with a comb of laser pulses, but it's much more practical if we didn't have a comb that was this complete. So we remove 2 out of every 3 spikes from this comb. And this is what we use to interrogate the temporal object. And well, this is just to show that it works. Actually, we use compressive sampling to do this work. So here we are using only 20% of the information that could be obtained, 30% to 40%. We're comparing what we measured in blue with compressive sensing. If you do raster scanning, this is very slow, but this is a reliable measure. And you see that even at 30% compression ratio, we use only 30% of the data. We get a very, very good agreement between what we measure and the raster scanning method. Our method takes maybe 30 seconds to make this trace. If you raster scan, it takes several minutes. So there's a real advantage to using this method. Next thing I want to talk about, not quite sure where it fit in with this talk, but it was so neat that I needed to tell you about it. We're studying 4-wave mixing in a zero index material. And if you do 4-wave mixing, here are 2 input photons, and they generate 2 output photons going in the same direction. Maybe these frequencies are different from this, but it occurs in the forward direction. What we found is that if we do this in an Epsilon-Near-Zero material, we can observe the backward process. That 2 input photons couple to 1 forward-going photon and 1 backward-going photon. You say, how in the world is that possible? How can that be phase matched? Well, phase matching means that the wave vector difference, that the total wave vector of the interaction vanishes. But when the refractive index vanishes, then K automatically vanishes, and the process is automatically phase matched. Now, what is the significance of this result? Well, it means that if you use ENZ materials, nonlinear optical processes that were previously believed to be too weak to be useful can excite you. So it's given us another tool to implement nonlinear optical processes. Okay, it's always good to show students, so forget about him. So Boris is the postdoc in the group, and here are 2, let's say 3 undergraduates, although I think Nicholas was maybe still in high school when he started in the group. Okay, so what is this all about? Well, if you want to access if you want to access ultrafast response of some material system, you need ways of addressing the system that rapidly. Trouble is that spatial light modulators have a refresh rate of maybe refresh time of maybe 30 milliseconds. DMDs are faster, but not that much faster. So Boris has been working on ways of using electro-optic modulators. First trick here, he has a fixed series of holograms. The laser beam comes in, the acousto-optic modulator, we put a grating on the AOM that can selectively diffract the light into this, or this port. So that's one thing we were working on. Other thing we were working on is we use the AOM itself as a grating. So here is an input beam of light. Here is a electrical signal from an arbitrary waveform generator. This creates whatever pattern we want, and the laser beam diffracts off that pattern. So we found that we can do highly accurate generation of arbitrarily complicated beams using this method. Okay, other thing we were working on is, well, I'll call it phase conjugation. Although phase conjugation is also known as generation of time-reversed wavefronts. So traditionally one implemented phase conjugation by some nonlinear optical process. This just illustrates how phase conjugation works. Beam of light goes through one medium, gets distorted, reflects from a phase conjugate mirror. The aberration is removed in the second pass. Now, the nonlinear optical method works fine, but is highly inefficient. So the conjugate wave that's generated is usually much weaker than the signal wave. So what we've been doing is to implement digital phase conjugation. Digital phase conjugation, well, Alice wants to send a message to Bob. Bob first sends a probe beam to Alice. This probe beam will experience any aberration between Bob and Alice. Alice then collects this pulse of light. She uses standard methods to measure the amplitude and phase of this pulse. She then turns on her spatial light modulator, sends a pulse that is the complex conjugate of the pulse amplitude that she had measured, and the pulse then looks distorted here, but is entirely undistorted when it arrives at Bob's receiver. Oh, and here are some results. Let's say we're looking at a Laguerre-Gauss mode. This has a circular structure. When Bob sends this, Alice receives something that is entirely messed up. She implements this process and gets back exactly what Bob had. She gets back the undistorted image. This also works for Hermite Gaussian modes as shown here. So this is very intriguing. For years and years, people were talking about phase conjugation and trying to make better use of it. In the meantime, optical technologies have developed to the point where it is effective to measure the wavefront and then generate the conjugate of the wavefront that you receive and then send it back to the other party. Okay, where are we now? I guess I'm done. Okay, so just a few remarks in ending. Extremely interesting physical processes can occur in ENZ materials. ENZ materials, including metamaterials, metastructures, display extremely large nonlinear optical response. And the huge nonlinear optical response of these materials lend themselves to many important applications, especially applications involving time-varying media because of the very short response time of these ENZ materials. If I didn't say so before, the visuals of this talk will be posted at my website, probably by sometime this afternoon. And well, of course, I want to thank all my students. I have one research group in Ottawa. I have one research group in Rochester. Many of the faces have changed, but I guess the group is roughly the same size now as it was 2 years ago when we took this picture. So I'll stop there, and I will thank everyone for your attention.
Thank you very much. We're always missing the clapping in the remote videos, but thank you very much. It was a very inspiring talk, covering many topics. I see that while people warm up with a question, maybe I can ask you one. Oh, there's already one. Okay, then Sudeep, do you want to read it yourself, or shall I?
You're
Sudeep?
talking to me or someone else?
No, to the
Hi.
question. Yep.
Good, because I don't see the message.
Hello, Professor Boy. Thank you for your great talk. I have a quick question regarding the ITO nonlinearity.
Yes.
So it was the science paper where the refractive, the N2 effective is, I think, 0.11 per centimeter squared per gigawatt, 0.11 centimeter squared per gigawatt at 60 degree angle of incidence.
Yes.
And you were using 66 gigawatt per centimeter squared. So if I just use the simple nonlinear equation that connects this change in refractive index with this effective nonlinear refractive index, then the change in the refractive index will be 7.26. So I'm wondering, like, if you guys have done the experiment, reflection and transmission experiment that you did in 30 degree incident angle, like if you have done it at 60 degree, would we see the same change in refractive index on the experiment?
Okay, I didn't mention this because this is not really supposed to be a talk about Epsilon-Near-Zero, but we measured N2 as a function of the angle of incidence, and we found that N2 is increasing with the angle of incidence. And there's a very simple explanation that accounts for this. It's just the standard boundary conditions that give rise to the Fresnel reflection coefficient. These standard boundary conditions say that the field inside the material will be much stronger than the field that's applied to the material from the outside. But I'm not sure that I answered. I'm not sure that that was your question. There were a couple of points that you made.
Yes, so the change in refractive index at 60 degree, if I calculate it using the simple equation, then it will be 7.226, right? The delta N. Okay.
Can I suggest that we continue?
This type of public forum is not a good way to deal with this.
Okay.
Yeah, I agree. I suggest we continue offline with the calculation.
If Zahir is in the audience, maybe he could try to answer. He was the first author of the paper.
I already answered it.
Okay, thank you very much. And Iwan,
yeah, thank you.
Do you have a question? I saw your hand.
Yeah, sorry, I couldn't figure out. Oh, sorry. Yeah, sorry, I couldn't figure out.
Sorry, I will mute.
Okay, sorry, I couldn't figure out how to type the question into the box. Maybe we can't do it as panelists, so I just raised my hand.
Please ask it. Yes.
I was very interested in your idea, Bob, about the terahertz measurement. I thought that was really a neat idea. You mentioned the fact that the entire terahertz trace there takes 30 seconds to measure. And I was wondering what is actually limiting that, because if you were to be able to measure at the DMD rate, you should be able to measure even without compression at thousands of points per second. So what is it that's actually determining the 30-second measurement time at the moment?
Well, as one might guess, I was not in the laboratory with the students while they were doing this. I see your point. That could be even better. So I don't know.
Right. Okay.
To me, a few seconds is very impressive to do this.
So what was going through my mind is if you did manage to get it to that sub.
Oh, I think I know the answer. It's the refresh rate of the DMD. The DMD, you can at best has a refresh rate of 10 kilohertz. Mm-hmm. So it just takes time to place enough patterns on the DMD to implement this strategy. That is what I think the answer is. I'd have to think about it.
Yeah, but even if you have 10,000 points that you're measuring, then you should be able to measure those 10,000 points in 1 second. That's kind of what I was getting at. I mean, the only reason I was pointing it out is if you really optimize that, it could become competitive to the current best commercial available measurement solutions for this problem. I think there really is something there to it.
Well, that thought had occurred to us. This was done in Rochester. University of Rochester Patent Office was not interested, which put us in a great position. We could patent it ourselves, pay for it ourselves, but unless we were also willing to start a company, maybe nobody would use the patent. So to answer your question, yes, I am also very pleased by this result. And in truth, Zhepeng Zhao, the first author, I mean, this was his idea, and it's a great idea. And we've maybe just touched the beginning of the usefulness of this.
Okay, thank you.
Thank you. If there's no other question, maybe I can ask you a more general question. I don't see any other. I would be curious to hear your opinion about the future of the field a little bit. Like, what do you think is a challenge now? Is the material that we need better material or better way to process them, or is it theoretical understanding, or what's your feeling?
So maybe I didn't hear the first few words of the sentence. What's the best strategy for doing what?
What's the challenge for the field of time-varying metamaterials?
Okay. Yeah. So well, make them faster and lower loss. I mean, this has always been the issue. Mm-hmm. I think the theorists are keeping up, but theorists are reluctant to work too hard on something that maybe will not be implemented in the laboratory. So I don't see the theory as being the point. It's almost always the materials. I think this is another materials issue, that we want a material that is faster and responds more strongly.
I see. Thank you. I see there is a. Oh, there's not a question. So there is a question from Fyodor. Can we do that as a last question? I think we have 1 minute. Do you want? Should I read it, or do you want to read it yourself, Fyodor? Well, then
okay. Can you hear me?
Yes.
I hear you.
Thank you for the talk. My question is there any special simulation techniques which are more efficient than FDTD for these time-varying materials, or maybe there are some theoretical approaches to study time-varying systems? Thank you.
Okay. Well, I'll let Zahir answer as well. We use a variety of methods: commercial software, MATLAB, numerical, and just standard programs. Zahir, do you have a better answer?
Well, the answer to his question is really depends on what you want to do with it. What do you want to do with? What do you want to simulate? If you want to simulate the field, FDTD is still probably the best way of doing. Or you can use console, where you can define, I think, time-dependent permittivity or something. Or you can do a lot of problems that, say, Maxime showed. You can solve analytically to really see the insights. So, or analytically, or using simple numerical methods using MATLAB or Mathematica. So. I guess this question, you can also ask this question to Professor Engeta. I mean, they do a lot of simulations on time-varying medium. So he's probably will give you a much deeper answer than I could give. Thank you.
Thank you very much.
And so I think we should close this session. Thank you, Robert, very much for the talk, and all the other speakers for today's event. And I pass the mic to Emanuele. Emanuele, are you there?
Hi, Ricardo. Yes, I'm going to briefly show
Thank you very
my
much.
screen. Can you see my screen?
Yes.
Yeah. Right. So thanks everyone for coming. I'm just going to thank again the co-organizers and also all the speakers and chairpersons. And finally, I just wanted to remind you that in a month's time, on the 30th of June, we have the final event, which will include a plenary talk from Professor Mordechai Segev, a GatherTown interactive poster session. So this is, we will all be, let me remind you, we'll all be on GatherTown. So the session will not happen on Zoom. It will entirely be hosted on a new session. And actually, as we speak, Yauting, our co-organizer, is actually preparing the venue for our virtual venue for the next event. So the whole workshop will happen on GatherTown. And there will be 2 poster sessions. And finally, the closing part of the final event will be a final roundtable, which will include Rachel Won, Raquel Rayo, Sebastian Schulz, Nero Ngueta, and Geoffroy Lerosé in the panel. Again, if you want to submit any questions for the panel, you can do that. You can do that on our webpage. And that's all. And I look forward to seeing you in a month's time. Thanks, everyone.